Okay, so in this video, I want to give you guys some intuition about transformers, or actually about the attention mechanism in transformers, in the transformer architecture. And actually being more specific, if we check the paper, this is like the full transformer architecture. Uh, the portion that I'll be implementing is this one, which is called cross attention. And the reason is because we are here crossing embeddings from the inputs and embeddings from the output. So for a language model, for a translation example, we would in this portion be comparing like one language with the other, like sentences. And in my example, I'll be using as inputs like a very small sentence in English, and as output, like the embeddings outputs that I have here that I'll be combining, I'll be using the translation into Portuguese. And here on purpose, I'm using a translation in which we have three words which could be translated into two words here. I am would be equivalent to sou in Portuguese, and happy would be equivalent to feliz. And like to start, here I won't be covering the rest of the details here. I can maybe cover in a different video, but like just to summarize what we have here as both inputs and for this on this side and also inputs on this side are like embeddings, and more specifically transformed embeddings. Our input, like the sentence, is going to be transformed into a matrix of words, which we call embeddings, and multiple linear transformations are applied here, but we still get the same shape. So both here and here will get as inputs from this side and this side will get representations embedding representations of each sentence. So in this example, as you guys can see, I'm using here random numbers, but like in practice, those numbers, they are like, since they come from embeddings, they are actually weights. They've been learned. And for illustration, I'm plotting here in a 2D chart that the sentence, like the words I am, they are like more similar than the word happy, because here both are more like related to the first person, and here the translation I'm also placing like in a similar position, and also the happy I'm placing more similar, like in a closer position to happy. And here I'll be replicating like the full, like the the equations that are applied here in the paper. They give details on two implementations, the scaled dot attention and the multi-head attention. Here I'll be implementing the scaled dot attention, and the main difference is that we have learned weights in like the input and output. So like maybe also in a later moment in another video I can like transform this into a multi-head attention. But like in short, what I will be implementing here is pretty much this equation, and this is actually the attention equation. And we have three terms here as input, which they call query, key, and values. Those terms comes like from information retrieval, and here I hope to give some intuition on how they work in practice. So we have here that there is this soft max of those two terms, and then they will be multiplied by this value. But here we need to know what will be like the query key and what will be the value here. And I noticed this wasn't clear in the paper. We only see that the input, two of the inputs come from two of the terms comes from the input, and one of the term comes from the output. And this I found in another tutorial, which I'll show in a minute. So in this tutorial from TensorFlow, and we can see like in the cross attention layer, which is the part we'll be implementing, then we can see that the target sequence, which is what comes from this side, is going to be the query, and the context sequence, which comes from here, are going to be the key and the value. So I'll be implementing here step by step on Spreadsheets, and the reason I'm using Spreadsheets is because it's a better way to visualize like the math and the numbers, like how the multiplication, so it's help to give some intuitions. So let's start. So the first thing I'm doing here is actually when I have like a given selection here, I'm giving a name here, input, and this is going to be my output. So like just to give some context, when I for example call input here and press Command Shift Enter, and this is a array formula, which isn't very common on Spreadsheets, but here I use a lot because it's more similar to how we would see in NumPy a operation. It's an operation that is applied to the full matrix and gives us output the full matrix. As you can see here, I'm giving context on this because I'll be doing a lot. So for example, if I multiply this by 2, then notice that the full input here, this full range that I named it here, is like multiplied by 2. So like as it was mentioned, so the query is going to be the target sequence, which is the output. So in this case, I'm just going to call the output here, which is the selection, and have it here. And then as input, if we see in the formula, we have the transposed of the key, which is our input. So in this case, we can just call the transpose of the input, and done. And here we need to multiply those two matrices. The multiplication here is, if you are not very familiar, there is a very good resource here that shows like how those multiplications step by step are applied. Here I'll be just using like the formula of matrix multiplication for multiplying those two. But pretty much what we have here is like those two numbers are going to be multiplied by those two numbers and then added, and then something analog is going to happen in the rest. And what we have here is something analog. It's not exactly the cosine similarity, but it's very analog to a similarity matrix. In practice, if those vectors that we have here are like all of them, if they have the same norm, like the same distance from the origin, or like if they are normalized, in practice what we'll have here is like a similarity of each one of those words that we have as target sequence and the words that we have as input sequence. So as you can see, we have here like higher values for like numbers that are closer to each other, like they have the similarity. So we see like I am here, it's more similar with so, and happy is more similar with feliz. And actually in the paper, if you apply this multiplication to like a embedding that is very big, those values they tend to be very large, and usually for neural networks we want small values, uh, because large values makes the gradients to explode. And in order like to do this normalization, we can divide by the number of the dimension of embeddings that we have. In this case, our embeddings have 2 dimensions. So the actual value that we would have here would be this matrix multiplication divided by the square root of 2. And let me finish here. Okay, so then here we have implemented what we have inside here. And then the next step here is to apply this softmax function, which we have in this side. And the idea of the softmax function is to convert all of those values into a proportion that would add up to 1. So it's like a percentage contribution. And we need to use this exponential function because sometimes we'll have negative values and sometimes positive values. So the idea here is to use the exponential equation in order to convert all of those values into positive values. So this is what I'm going to do here. So exponential of all of those values. So again, when I do like this array formula, then what we have here, this is the exponential of this value. This is going to be the exponential of this, and so on. So it's just a shortcut. So as you can see now, all of those values were converted to positive, and we divided this by the sum. In this case, it is actually the sum of each row, which I'm going to calculate here. So I just need to calculate this sum and then do the same for the bottom. And then finally, the softmax of this amount of this matrix is going to be this matrix divided by those values. So I'm pretty much like dividing all of those numbers, like 1.2 by 3.9, and then 2, and then so on. This is what I'm be doing here. And what do we have here? If you notice, all of those numbers here, they will add to 1. So it's like a percentage contribution of each one of those words here, embeddings, that you want to be propagated in this attention transformation. So after we get this softmax, we need now to get the value, like in which is also this input sequence. So I'll get here, and what will happen now is we'll be multiplying both in order to create this transformed output or transformed target embedding. And this is like you are telling that you want to create a transformed target embedding as like a based on how similar, like giving like some percentage of contributions from the memory, from the input that we have. So pretty much like, for example, for the word so, we have that we want 30% of contribution from the word I and 64% of contribution from the word am. So what do we have here? I'll do like step by step just to show how exactly those numbers are coming up. So it's this number times like this original vector plus this number times this original vector plus this number times this original vector. So here we have 0.7, and then here I have the same thing, but now for this second vector. So here, and then plus this term times this second vector plus this term times this third vector. So what we have here is like a new position of this vector so, which is going to be based on like those contributions. So since like the word I and the word am, they are more similar than the word happy, it's like you are like sending the vector like to a new position which is like closer to both of them. But again, like all of those values, those embeddings, they are learned, and then this transformation is applied in a way like uh, to to use the context of the sentence in order to give a new position to that vector. And here I can do the same calculation here, or I can just do m both here and multiply both of those vectors. And oops, and then I need to delete here. So here we have this new word so, and feliz, we have here that the new vector is going to have 70% of the original vector of happy, but also it's going to have like about 30% of those two vectors. So that's the new position of the word feliz. And that's it. So here we implemented this scaled dot product, and more specifically this cross attention, since we are like crossing this input and the target, and like this, the only like difference with the original, like what's implemented in the paper, is that there will be those linear multiplications, and also like for this case we don't have masks, but there will be like some attentions that they will have masks, or there will be like attention components that they will be like comparing the words with themselves. But yeah, that's it. I hope it was helpful to give some intuitions, and yeah, that's it.